Hi Tipti, and welcome to the second module in Advances in Image Processing. So this module is mainly going to speak about image preprocessing. So generally, what is meant by preprocessing? So preprocessing is a name used for an operation on images at lowest level of abstraction. So it is the lowest level of abstraction in image processing operation. So it's called pre-processing. Here we should understand that the input and output images are both intensity image. So you take an intensity image, apply the pre-processing, the output is also an intensity image. So to understand in further, the pre-processing, it does not increase any image information content. For example, if you speak in terms of entropy present in the information, in the image, then what does pre-processing do? The pre-processing would preferably, it will reduce or decrease the entropy present in the image. So, but what we need to understand here is that the pre-processing, it suppresses. When I say something information is reduced, what is irrelevant is reduced. That is, it suppresses the information which are irrelevant. So the aim in image preprocessing has an aim to improve the image data, that suppresses some undesired distortions, or it enhances some image features that is important for further processing. So basically what we do is, suppose we have an image, so we apply the pre-processing. Okay, so based on which we'll see in detail little later. So what we do is, it does not improve any information content, but whatever we have calculated, say for example entropy, the pre-processing may reduce entropy. What is entropy? It's actually the randomness. Okay, so the pre-processing might reduce. So it's not simply reducing. So depending on the operation, so it reduces the irrelevant information. Okay, so any undesired distortions. So that is why we need to go for image pre-processing. Okay, so that is the aim. So that is to suppress the undesired distortions and enhance some image features that is needed for further processing. So image pre-processing methods, there are many classifications. Okay, so some people, they classify the image pre-processing methods into image enhancement as one of the type, where image enhancement means we speak in terms of covering pixel brightness transformations, or do some local pre-processing, or even image restoration. So image enhancement, image restoration, these are all some of the major ways in which image pre-processing is usually done. So image pre-processing, there are mainly four categories. Okay, so four categories, and this categorization is based on the size of the pixel neighborhood that is used for the calculation of the new pixel brightness. Okay, so we are going to see that in the further sections. Okay, so basically a considerable redundancy of information in most images. So it allows the image processing to explore, image data itself, to learn image characteristics in a statistical sense. So these characteristics, they are basically either to suppress the unintended content or an unintended degradation such as noise, or basically, as we say, we go for image enhancement. Okay, since we are saying there is image pre-processing, we need to have some a priori information. So what kind of a priori information is present, that becomes very important here. So if the idea of the pre-processing is to correct some degradation in the image, then the nature of the prior information is very important. So what is this? So the first group of methods uses little or no knowledge about the nature of the degradation. So there are different. So I'm going to classify three. So in the first thing is, there is no actually a priori knowledge about the nature of the degradation. There is a second group which assumes that the knowledge of the properties of image acquisition device, for example, what kind of sensors you are using or what kind of cameras are using, so that a priori information and the condition under which that image was captured. Okay, so these kind of a priori information, some image pre-processing techniques will use. Okay, even sometimes the nature of the noise, there are different types of noise. So we say white noise, Gaussian noise, etc. So it's if we get to know the nature of the noise, what is the advantage we get? We can understand the spectral characteristics that can be used as the a priori information. Okay. Then the third kind of a priori information is that this pre-processing, it uses knowledge about the objects that are sought in the image. Okay, some information, some statistics about some object I need to process. So suppose I'm going for image segmentation, so maybe I need some information about that object. So that kind of a prior information, so that when I'm doing this pre-processing, I'll see through that the kind of transformation I'm applying during pre-processing does not it's done in a better way, so that what is needed is not disturbed. So if the knowledge about the object is not available, then of course during the processing, this one, there is pre-processing, then there is processing, then of course sometimes we go for post-processing. So during processing, in case in priori if we do not get, then during processing we need to have more focus. But in case you have a prior information, also in pre-processing we can take care of some of the aspects. So I told you that there are four categories of pre-processing. Okay, so the first category is wherein we go for pixel brightness transformation. Okay, so this is the first category. Again, in this there are two types. That is, under pixel brightness transformation of pre-processing category, there are two types. One is brightness correction, and the other one is grayscale transformations. So here the idea is that the brightness transformation, it modifies the pixel brightness, as the name suggests, pixel brightness transformation. So we say that the image has got some coordinates, and each coordinate has some intensity or brightness values. So here in the pixel brightness transformation, we modify the pixel brightness, and this transformation, it depends on the property of the pixel. So basically, as I told you, there are two classes. One is the brightness correction, and the one more is the grayscale transformation. So what is meant by brightness correction? Here it modifies the pixel brightness. So what it meant by modifying the pixel brightness? So original brightness is taken, and the position of that pixel of the brightness value is taken. So these two things are considered during brightness correction. What is that? One is the pixel brightness and the position of that the position and the brightness value at that position. So that is taken into account. So in the second one, under pixel brightness transformation, that is the grayscale transformation, here the brightness is changed irrespective of the position of that brightness value in the image. So we'll see them one by one. So coming to the first kind of transformation, or the class under pixel brightness transformation, is the position dependent brightness correction. So usually what I said is that the image acquisition device, like your camera, sensors, to be frank, the acquisition and the digitization device, that should not depend on the position in the image. So sensitivity of the image acquisition and the digitization devices, they should not depend on the position in the image. But in many practical cases, this assumption is not valid, because say sometimes what happens, the lens, it can attenuate more light if it passes farther from the optical axis, and there is something called as photosensitive part in the sensor. So it is not of identical sensitivity. So these are all the practical problems that arises when the capturing of the image is done. So uneven object illumination sometimes is also a source of image degradation. Okay, so considering if the image the degradation is of a systematic nature, okay, so then the degradation that we can suppress by means of this process known as brightness correction. So we use some mathematically a coefficient known as multiplicative error coefficient, that is E of ij. So this E of I comma j, it describes the change from the, so there is some ideal intensity level, right? So what is that change, or what is the error compared to the original ideal identity transfer function? So if that is the multiplicative error coefficient, that is the E of I comma j, then assume that the G of I comma j is the original undegraded image that we consider. So G of I comma j is the undegraded. So this one. So if this is undegraded, so if E of I comma j, what you can see here is the coefficient. So that is the error coefficient. Then what we can say is that the f of I comma j, that is the image containing the degradation, is the multiplication of the image function without the degradation with the multiplicative error coefficient. Okay. So basically this coefficient itself, that is E of I comma j, it is obtained from the reference image G of I comma j itself, okay, but with the known brightness captured, okay. So we can say that if at all the constant brightness value is C, then we can just multiply the G of I comma J with some C value. Okay. So the degraded result in the image, okay, so that is we call it as the FC of I comma J if considering the brightness constant is C. So then the systematic brightness errors can be suppressed. How you can suppress that error? Then I can say that it is equal to g of I comma j, that is I want to suppress that, is equal to f of I comma j divided by e of I comma j, where c if I have taken it as a constant, so I can say it as c into f of I comma j divided by fc of I comma j. So before going to the next type, that is the grayscale transformation, one thing we should understand that in the previous one, that is the position dependent brightness correction, so the second equation can be used only if the image degradation process is stable. So we are telling multiplying with by constant multiplication error, right? So we are multiplying G with E, which is a constant, or we can represent it by C. So it is not here also we have not taken everything into account, where there can be non-linearity also. Okay, so the best thing could be like during image capturing itself, if we can try to remove such kind of error, it's well and good. So we can go for recalibrating the device. So coming to the second type, where is the grayscale transformation. Here the transformation, it does not depend on the position of the pixel in the image. So consider the original image with the brightness P. Okay, so we say here P, the brightness, input brightness is P. So if the brightness is P and if the brightness is in the range say P naught comma Pk, so if this is the range in which the input image has the intensity or brightness levels, then we apply some transformation, say tau. Okay, so the transformation tau of the original brightness P from the scale P naught to Pk into the brightness Q. So if you want to convert from this, we want to going to transform, right? So transformation from P naught Pk to the range, say we'll say it as Q naught and Qk. Okay, so that transformation, if that is if the whatever is in the range input image range from P naught comma Pk, if you want to transform to Q naught comma Qk, then we apply this transformation. So that is tau of P gives you Q. Okay. So the most common grayscale transformation is what you can see in the figure here. Can you see the figure here? That is the figure 5.1. So what does this 5.1 show is the piecewise linear function A. Okay. So you can see a function A. So what you see, I'll put it here. So this is the piecewise linear function A. Okay. So piece may it is linear. So piecewise, you have here one piece of linearity, here one, then one discontinuous, then there is a change, again one piecewise linear, then again piecewise linear. Okay, so the most common grayscale transformation, that is one is the piecewise linear function A. So what does it do is it enhances the image contrast, so between the brightness values P1 and P2. So here if the input, so what you see is the x-axis is the input G, so from 0 to say 255. So if the input say is from 0 to P, then I make it constant, so it's not much. Okay, so whatever is there in the range P1 to P2, so this range, okay, I'll put it in yellow. So this range, so this range, whatever was there in the range P1 to P2, that is stretched more. Okay, so that is stretched more. So whatever was less than P1, it's not stretched much, but there is a sort of mapping. Okay, so we are doing some sort of mapping. If the input level is say something, so then the output is something. Okay, so the piecewise linear function A, it enhances the image contrast between the brightness values P1 and P2. Okay. The second function what you see is the threshold function, or we call it as brightness thresholding. Threshold is a simple one. So you have, I'll put it in say dark blue color. Okay. Can you see this is, okay, so this is the original one. It looks like, a step function. So that's a thresholding or brightness threshold. So we can apply transformation like this threshold. So if the input value G is less than P2, make it 0. If the value is greater than P2, make it 255. So whatever is there, either the value can be 0 or 255. So black and white. So what we can get is a black and white. So that is called as the brightness thresholding. and C, that is a straight line. Okay, so you can see ulta. Okay, you can see the ulta. What is this actually? It's called negative. So if at all input is white, the output should be black, right? 0 make it 255, 255 make it 0. It's finding like the image negative. Okay, in the olden days, if you see the camera reel, so we call it as negative, right? Negative, we go and process it, right? So the negative is like whatever is black, make it white, or whatever is red, or maybe I think the opposite negative of I do not remember it. So you find the negative. Okay, so maybe what is gray, make it more white, or something like that. So make it negative. Okay, so it's like making 255 minus the original value, that is a negative. So that has a negative slope, what you can see here. Okay, so that is about the one of the thing, that is the grayscale, three types of grayscale transformation. Okay, so when we speak of digital images, they have a very limited number of gray levels. So the grayscale transformation, it's like you just have a lookup table and you can do this. Okay, so the original brightness is the index to the lookup, and the table content should give you the kind of the new brightness level. So you can have this kind of thing possible. Okay, of course, this is when I'm speaking of grayscale images. That is when you have no colors, so you have just the two-dimensional. If you add the the color components, or like if you have go for the dimensions, like usually we go for three, XYZ or RGB or CAN or YCR. So the same principle can be applied for color displays. So a color signal usually consists of three components, correct? So the red, green and blue. So you can have three lookup tables, so something like that. Okay, so these tables are called as actually the palette in the computer terminology. Okay, so the grayscale transformation are mainly used mainly when the image is viewed by a human observer. See, the finally the judges of the image are the humans, because finally image should be perceived by the humans, and we should be able to in image processing, final the judge is ourselves, the human eye. So we need to get a better picture or the better image, something like that. So if you think of an X-ray image, okay, you want to make it much clearer. So maybe after transformation, it becomes more clearer. Okay. So if the transformation mainly, or the grayscale transformation for contrast enhancement, that can be done automatically using histogram equalization technique. So what is this histogram equalization technique? So the aim of such a technique is to create an image with equally distributed brightness levels. So what is an histogram basically? Histogram means for the different, how many pixels have this intensity level. So if I say intensity level is say pk, so what is the value n, how many pixels in that image have the intensity value, say pk, that n value. Okay, so basically, if you go for histogram equalization, so that is histogram. If you go for histogram equalization, so we can, try to equalize the image. That is, we can distribute the brightness level. So now that you know which pixels have which brightness, how many pixels have which brightness level, so we can, try to equalize it. So we can try to spread out or distributed the brightness levels over the whole brightness scales we can think of having. So histogram equalization, it basically enhances the contrast, okay, for brightness values. So close to the histogram maxima, and whichever is close to the minima, so it decreases the contrast. So as you go close to the higher value, the contrast increases, and lower contrast, the contrast decreases. Okay. So what you can see here in front of you is a figure which demonstrates a simple way, it demonstrates histogram equalization. So what you see is here it is varying, okay, histogram varying. I'm trying to equalize it. So over different q values we're going to spread it. So we spoke of the transform tau, where the input is say p and the output is q. So let us describe the, basically just now I told about histogram. So the histogram, we can treat it as a discrete probability density function. Okay. So the monotonic property of the transform tau. So whatever the monotonic property tau implies the first equation, what you see 5.4. Okay. So that's what you saw just in that image now. So if the h of pi is the input, so the output, the transformation is given by g of qi. So the equalized histogram g of q, basically here the probability density function is a uniform distribution. So, and the value of the function f, that constant you saw just now, no, in the previous image. So, f is given by n square by qk minus q naught. Rather than just saying it mathematically, let's try to understand here. So, what we are going to do here is the qk is the maximum minus the minimum. So, that is the denominator. So, we get the range, right? So, that is the n square is divided by that difference for an n cross n image. So if you're thinking of the idealized continuous probability density function, then we can substitute the equation 5.5 in equation 5.4. Okay. So what is that? And we can derive like this. So n square integral from q naught to q. So that into 1 by qk minus q naught ds is n square. We can actually bring that out and we can represent in terms of h of s ds. And from which tau can be derived like this as q is equal to tau of p is equal to qk minus q naught by n square. Just write it down and just express and just do the manipulation and you'll get this equation. I want you to try it yourself. It's very simple. Okay, so now that you know, so the integral what we saw in the previous equation as the actually that is known as cumulative histogram. So the area under the histogram curve is known as a cumulative histogram. So area is nothing, integration is nothing but area. You should understand that. So the integral what you saw is nothing but the cumulative histogram. Okay. So that is the thing. So next coming to the algorithm. So finally what is your histogram equalization? So what are the steps? So the take the input image. So n cross m image. As say it has got some G gray levels. So let us initialize an array H of length say G and let us make it initially 0. Then we form the histograms. How to form the histogram? From top left to bottom right, we scan each and every pixel and see how to find the histogram for each pixel. What is the intensity value? So for a different intensity, how many pixels have that intensity? So then perform h of gp is equal to h of gp plus 1. So we give g min be the minimum g for which whatever the intensity value is usually greater than 0. So then we form the cumulative histogram. So cumulative is one by one we keep adding. Initially to one value to itself, then the second value add to the first value, third value to the added of 2 and 3. So 3 to 1, add 3 to 1, then add 4 3 to 1, 5 3 to 1. So you go on accumulating, cumulatively keep adding. Okay, so that's what is meant by cumulative image histogram. Then you set the set the value t of g is equal to, you round it off. Okay, then you rescan and write an output image. So basically we are taking the image, we are performing how to perform scan, then find the cumulative image histogram, then take the minimum of that. So h min is equal to hc of g min and set this value. So once you have setting a threshold value, so this t is a threshold value, so then I round off. So depending on that, so based on this equation, I round. Again, so once I know the histogram, I have to see. First, it's very simple. I'll tell you. So first, find the histogram. Okay, by scanning. Okay. So then you find this threshold value. So for each pixel value, what we do is we calculate what is the transform value after image equalization using this equation. Okay. So then what we do is rescan the image and write an output image with the gray level GP, and this is how we set the output histogram equalization. Okay. So this is one example wherein the histogram equalization is applied. So take the original image, you can see that is a lot of contrast is there. So I'm spreading the intensities. Okay, so spreading the intensity. So what you get B is the equalized image. So basically in terms of graph, this is how it's happening. So you have the intensity spread out like this. Okay. So then I'm making it, spread out. So this is how the original histogram is, whereas the intensity and frequency. Frequency means how many of the pixels have that value. Okay. You can see that the more of the pixels have, I think around 220 something. 24 or something. So also near 128, the number of values, number of pixels in an image. So many have them. Then after equalization using the formula, this is what you get. So this is about the first topic. So basically in this module you have 3 topics. So I've just completed the first topic. So the next topic we will study in detail about the geometric transformation. Okay. So see you in the next class.